Really fun. It's fun, but I'm playing freaking.
Hello and welcome to today's webinar. My name is David Cash. I'm a member of the marketing team here at Mountz. I'm glad you've taken the time to join us today as we look at another topic in our efforts to help in your processes. And so today we're looking at how we can collect and analyze torque measurement data. Now, there is quite a number of different things to talk about within this particular topic. So let's go ahead and jump right in it. But first, if we talk about basically the value of being able to have our torque measurement processes, if we have visibility on those particular items that we are testing, this gives us the ability to actually measure and be able to look at the different tools and processes that we have in place that allow us to be able to make good decisions regarding our torque tools and our process. And so another value within the process here gives us a chance to take a look at specific tools that we are looking at, the calibration cycles that we are looking at. Also, we can look at any type of root causes that may be happening from specific tools as we measure those tools within the different steps or processes that we have in our overall assembly process. We also then have the ability to have documentation around the tools that we are testing, the items that we may need to help for any type of ISO audit or continuous improvement audit. If we have all of that information documented, this can really help in those types of situations. And then finally, we can look at the how a specific tool performs over time. How accurate is that particular tool? Is it drifting? All of these types of things give us value when we are measuring our particular tools within our stages of the process. And so there are a number of different stages within the assembly process that we can use. Our torque analyzers to help us to be able to, again, capture that data that we might be looking for to help us in analyze the process to help us improve. And so we have prior to the assembly, when a tool is being used, we have during the assembly process, and then we also have after the assembly process. And all of these areas allow us to be able to use our torque analyzers with different types of sensors to be able to capture and pull in that specific data that, again, can help us in creating better plans or giving us, again, visibility in certain areas to help us make improvements in our process. And so prior to the assembly, we have our tool setup process. We have the ability to do tool capability studies and R&D. During the assembly process, we're looking at doing torque verification or torque validation in between calibration cycles. And then after the assembly has been done, we can also use our ability to grab data with our torque analyzers to do torque auditing on specific fasteners or also on tool recalibration. And again, providing us with traceability within the entire process. And so that's going to kind of lead us into our poll question for today. And that poll question is, how do you use torque measurement data currently? Are you using it just for calibration, traceability, and documentation? Is it being used to evaluate tool performance? Are you using it to evaluate fastener processes, or are you doing all of the above? And so this can give us a good snapshot of where we are within what might be helpful for you as we look at these different areas within the presentation. So we'll give you just a minute here to answer these questions, and then we'll go ahead and continue with the presentation. All right, let's go ahead and take a look at what the results are. And so it looks like about a little less than half of you are doing all of these types of testing, followed by tool calibration and traceability with the documentation as well. And then bringing up the rear is tool performance and evaluating the fastener process. So thanks very much for participating in that question. And this will kind of, again, lead us into the different areas of the actual processes that we can do testing with. And then the first one we talked about was being able to set up a specific tool. So if you are changing one tool from one area to work in another area or another application, that tool may need to be reset and calibrated. Obviously, we can do that with preset hand tools, adjustable hand tools, as well as power tools to be able to set those up. And so in this case, we want to use an analyzer that can, in this case, would be one analyzer that has a built-in transducer with the ability to capture that data. Or it could be an analyzer like this that also has a built-in sensor or the ability to add additional sensors to it. And that can be used, again, to set up hand tools or even a power tool. In this case, we would be using a rundown or joint simulator in this case to be able to set that power tool up. But these tools can be added, or excuse me, this type of analyzer, we can add different types of sensors to that. We'll take a look at some of the other sensors that we have relating to either a reaction style transducer or a rotary style transducer. But in the tool setup, this gives us the ability, again, to be able to capture data in either type of analyzer. And we have the ability to gather that and export that with time date stamp and things like that. Now, during the torque verification and torque validation process, this is really important because this allows us to be able to check our tools in between the calibration dates that may happen if you are working off a system that allows for your calibration that is done on a periodic basis, whether it's 6 months or 12 months. No matter how much the tool has been used or how little it's been used, we always send it out at a specific interval for its calibration. And one of the worst things that you want is to get your tool back and the as found condition of that tool is out of tolerance. And so this can create a tremendous amount of headache, can create a tremendous amount of cost and burden as you look at what information or what applications this tool may have been worked on, and is that going to cause any ramifications about parts that may need to be returned or components that may need to be reworked and things like that. So during the torque verification process, we have that ability to be able to check a tool during the actual time in between the calibration dates. And this can be done based on a weekly requirement, a monthly requirement, could be a shift requirement, but whatever frequency may work best for you. But this can be done again with the use of a portable analyzer with a rotary style sensor. And so this type of sensor goes in between your tool and your application, and it allows you to be able to measure the tool actually in use on your part. And so this gives you a real good representation of what is happening actually on your part. Now, this value can and sometimes is different than when you test it on the analyzer with the joint simulator. But again, this gives you that ability to validate and verify that your tool is producing what you want on your part. And again, the analyzers have the ability to capture that data with a time date stamp and information regarding the tool for you to be able to collate and use in analysis down the road. Now, we do also have another function that is very useful in this, and that would be the use of a barcode scanner that can be hooked up to the analyzer. And so in this case, we have our tool here with a barcode. We can go ahead and activate the barcode by the use of our tool test function, and then we can hit select test. This is going to power up the barcode scanner. Then we can simply just grab the scan of the tool. That's going to automatically set up a tool test that we have already pre-loaded onto the unit. This gives us the parameters of a lower spec limit and our higher spec limit, and the number of readings that we're going to take. And so as we take those readings, you can see that our light status light goes from red to green. And as long as the values are within the green area, then we can simply just follow the lights, and we don't necessarily have to do anything else as it relates to the tests. If it's going to be a situation where you're doing a number of different tools and different tests, and you just want to make sure that all of the values that you are reading are still within the spec. Again, the tool test type of function gives us the ability to capture tool data with a time date stamp. And then again, we can pull up that information and evaluate it over a period of time to make good decisions about when we calibrate or how we calibrate those tools. If we need to increase the frequency, or if possible, we can decrease that frequency, or we only will calibrate this tool once we see it moving out of the specification limits. With that, that would be kind of during the torque verification and validation process. Now, you may hear the term often static torque or dynamic torque. And so they're a little bit different scenarios in where they can mean different things. Primarily, when we look at dynamic torque, this is when we are measuring the torque during the assembly process. So we're turning the fastener, and then we will take that until that fastener has been torqued, and we're measuring that. And that can simply be done with the rotary style sensor that we looked at. And then the static torque is when we are measuring the torque on the assembly, or measuring the fastener after it has already been installed. And we do this by turning the fastener a few degrees with a wrench or an assembly tool. And so that is primarily the definition of the static versus dynamic torque. However, there are situations where you may run into a context where we're looking at either using a static transducer or a rotary style transducer. So in this case, our BMX transducer here does not turn when the tool is put into the drive. Or if we are using a rotary style sensor, this completely spins and allows the tool to be used. And so in this case, we're looking at sensors that could be considered a static sensor versus a dynamic sensor. And then we also have the tooling that will be considered either static or dynamic. Again, either a power tool where there's continuous rotation or a hand tool where there isn't that continuous rotation. And so those different areas you may run into as it relates to being testing dynamically or statically. So when we look at the actual torque auditing process of this, this is primarily where, again, we would be using a rotary style sensor with a torque analyzer. And there are a number of different types of tests that we could run with the torque process or the static torque process. And that would be either the first movement test, the loosen test, the marking, and this is all kind of also under the umbrella of trying to measure what the residual torque is. Now, there is really no residual torque in a fastener once it tool has been removed from it. However, there may be some slight torque in that, that there may be some torsion, and we'll kind of talk about that here in just a second as well. But if we take a look at the first movement test, what this means is that we're actually going to take the fastener and we're going to turn it in the tightening direction a few degrees of movement. So anywhere from about 3 degrees to 10 degrees of movement is where we would like that particular fastener to go. And so there are some issues with this type of test. And if we look at it graphically, it may help us to better understand it. So when we apply our torque, we have our torque and angle at this particular point. Now, if we want to try and move this fastener or get it started moving again, it's going to take a little bit of effort to do that. And we also need to look at kind of the coefficient of friction that is going to play a part in this as well. And again, the coefficient of friction is we're looking at what the amount of force is to move something at a constant rate. But typically when we do this, we're taking something that is static and we're moving it. It generally takes more force to get it started than the force is while it is moving. And so once we overcome that threshold of motion, we have our constant friction. And so in this case, when we're trying to use our first movement test, we actually may generate a more or higher torque to get that fastener started. And then after about 3 degrees of movement, we may see a drop. And then depending on where the auditor stops, the wrench will be whatever the torque is after the specific test. But that typical value we want to measure is, again, between 3 to 5 degrees of movement. And that can give us a good representation of what the applied torque was at the moment of the assembly process. Next is going to be the loosen test, or sometimes referred to as breakaway. But we are simply then loosening the fastener and we're measuring what that torque value is. Now, in this case, as I mentioned, Sometimes in the fastener, there is some torsion that is built up, and you can actually see a lower torque value measurement because of that torsion that is in the fastener is helping us when we're trying to move that fastener or break it away in the loosening direction. And so that can play a part in it as well. So sometimes you will see that a fastener will take less torque to remove than it was to install it. And that's typically what is going on here. And then finally, we have the marking test where we put a mark on our part and we also mark the fastener. Then we will break the fastener away and then realign the fastener to the line on the part and measure what that particular torque value is. And then in that case, or in the case of all those particular tests, if we develop a correlation or an uncertainty value with the assembly torque versus what the auditing torque is, we can then say if we're getting X during our audit, we know that during the assembly process, we are seeing what we'd want. So there would need to be some testing done during the assembly process to capture what the actual torque was when the fastener was applied, and then develop an uncertainty value or a correlation between what that value is at the auditing process based off of whatever test you might consider. Which test is going to be best, and that is going to be dependent on which test you think is going to provide you the best results. In all of these cases, there's going to be some type of change that may occur because the friction values are going to be different. The material may do some different things than it would have done during the assembly process. And so in any event, you would need to kind of develop those uncertainties. And you can do that by capturing the data from during the assembly process and then also during the auditing process as well. So that's going to bring us to the process control and tool capabilities portion here of what we're talking about, and that will kind of lead us into the discussion of CP, CPK, and then also CM and CMK. And so when we look at what the difference is between CP and CM, CP is looking at your entire process or the process that you have in place. And then the CM and CMK deals with the actual machine, or in this case, the tool that we're using, and we're measuring that. And with that, there are some different requirements as it relates to how you test for CM and CMK. Typically, you want to do a value test of about 30 to 40, or excuse me, 50 rundowns continuously without any breaks. If you are doing it with an operator, you want to make sure that you're testing with the same operator. And again, that it's a continuous type of test to testing for our CM and CMK. The CM value itself is basically if we have a target, or excuse me, we don't have it's just basically grouping the actual readings from the test and how closely those values are grouped together. When we look at CMK, the values are how close they are together in relationship to the actual target that we're trying to hit. So that's basically the difference between CM and CMK. And so if you have an analyzer that will do this automatically for you, that certainly can be helpful. So in this case, I have the Easy Torque 3. And if we put our tool setting at 10.8 inch-pounds and with our tolerance at plus or minus 6%, that's going to give us our min value and our maximum value there at 10.15 and then 11.45. We can go into the advanced view and then we can go ahead and take our readings. And so I did this a few days ago, and this just so we don't have to uh, bother with the setup and the changing, but nevertheless, so I went in and we took 40 values, and again, these are continuous that we are looking at, and the analyzer itself is compiling the CMK values, the standard deviation, the average, your min, and the max that you would be testing for. And all of this information is then stored locally on an SD card, and you can export or just remove that card and pull that data straight off there. If we wanted to, we could add the tool serial number in the data field as well. So that could be captured here. But you could see the values that we achieved are really, really quite good for this. We want to see a CM value above 1.33, our CMK above 1. So at 2.7 for our CM and 2.55 for our CMK, this is a really good and an accurate tool for us. And so with the actual data that we're looking for, we've probably all seen the distribution curve, but when we're looking at values that are closer to 1, this is kind of the graph that we would be seeing, even though that there are some on this particular graph, we may see some data points that are out near the 3 sigma mark, but this would be the example of that. But we want to try to move our distribution curve more to where we're getting more readings around our mean or target value with this. And as we can improve our CM or our CMK value, in this case, we may see a more representative graph that looks like this, where if there is a shift in the sigma, either 1 or 1.5 degrees of shift within that, we are still well within the lower spec limit and the upper spec limit. So the higher CM K value we can have, the better we can rely on that particular tool providing the torque values that are being produced. And so with the CM and CMK testing, what this really does, it allows you to be able to focus on the process. So if you are given the task of trying to improve a specific process and you're trying to measure what that is, the first thing you'd want to do is measure the tool that you would be using with your CM and CMK values. If you do see a CMK value that's under 1, you know that you can start with the tool itself. There may be some issues with that tool. It may need to be serviced. It may need to be recalibrated. There are some other factors that may be with, the material that's being used. It could be the operator or the process, but if you are seeing that CMK value under 1, then this gives you the ability to focus a little bit more on the tool itself rather than the environment, what's happening around the tool. And so conversely on that, if you are seeing a CMK value between 1 and 2 or above, then you know that you can look at the external factors that may be contributing to the process. So are there differences in how the tool is being used from operator to operator? Are they setting up this tool or using it within the process that might be different? So it really can help you give a direction on what you need to do to try to improve the process. And that would be when you are using the CP and CPK measuring of your actual process versus measuring the tool itself. But when you do the CM and CMK testing, again, this can really help guide you in taking a look at your process and how and what you might want to try to address first to help tighten up those particular numbers. So again, with that, all of those different types of tests, we've got analyzers that can, again, be used on the floor, that can be used within the lab, and that can be used for auditing after the fact, along with different sensors that can be used with those particular analyzers as well. We can time, date, stamp all that information, and you can gather that data and again, have an opportunity to make really good decisions regarding your process. And so with that, that's going to lead us into our question and answer section. So if you have any questions about this topic, then we can go ahead and you can enter those into the chat and we can go ahead and look at those. So Chris, do we have any questions?
Hi, Dave. Yeah, we have an initial question. What is the difference between a tool's accuracy and repeatability?
So that is going to fall under the CP or the CM and CMK. The CM value is measuring how accurate the tool, or excuse me, how repeatable the tool is. So it's taking all of those data points and looking at how closely those are grouped. And then the accuracy looks at how those particular values are grouped in relationship to the actual target that they are trying to achieve. And so when we look at the calibration process, if we are seeing a tool that is very repeatable, however, it's not being repeated at the value that we need the tool to be, then we can make an adjustment to the tool itself and then move that into the right calibration. So we are getting accurate readings at the target. So that is basically the difference.
All right, thanks, Dave. Next question is, what are the benefits to measure angle when you're measuring torque as well for an application?
So again, when we're measuring the use of angle in the auditing process, if we want to do the first movement test, that can be very helpful. We don't want to add too much angle or turn to the fastener to help increase the actual torque that's being used. It can also be very useful in monitoring when a fastener is assembled. So we make sure that a fastener gets the correct amount of turn. And this can be useful when using different styles of tools where we can actually measure the angle during that process. We can detect any type of cross thread issue or a possible stripping issue. So in those cases, measuring the angle can be very helpful.
All right, thanks, Dave. Next question is, on the torque verification process that you mentioned, is there a recommended interval to follow on testing a tool? Is it weekly or something like that?
So primarily it's going to revolve around internal processes and what you may think is going to be sufficient. Again, it could be if you do have tools that are set up on a 12-month calibration cycle, you want to test those tools twice a month, once a week, or once a shift. It basically comes down to the critical nature of the application, how much work or rework might be required if there is a tool that is found out of calibration. So those types of factors can play into the frequency that you might need for that type of testing.
All right, Dave. It looks like that was the last question we got.
Awesome. So thank you very much again for joining us for this discussion. If you have any questions regarding our torque measurement, feel free to jump onto our website at mountztorque.com where you can get more information there, or you can speak to either one of our applications engineers, or we can also get you in touch with your particular salesperson that might be able to handle you. So very good. Thank you very much again, and we'll see you next time.